Hello, I'm Emmanuel from Sophosport, and I'll be teaching you the fundamental concepts of domain name systems or DNS. Today, I'll give an overview of DNS function, illustrate the DNS components and the overall resolution process, and explain the DNS structure and hierarchy. I'll then walk you through the DNS query process and query types, including a brief discussion about DNS forwarders and time to leave. And finally, I'll cover the common resource record types you'll encounter. Links to all relevant resources can be found in the description. Let's begin with the DNS overview. DNS stands for Domain Name System. It's a fundamental technology that facilitates the translation of human-readable domain names into IP addresses used by computers to locate and communicate with each other on a network. As the backbone of Internet navigation, DNS servers provide a hierarchical and distributed method of translating fully qualified domain names, or FQDNs, into IPs. The primary goal of DNS is to simplify the way users access resources on the Internet or internal networks and eliminate the need to memorize complex IP addresses. For example, it's easier to remember your favorite website by its name, sophos.com, than the address 184.30.150.202. Think of DNS like a telephone directory. You search for a name and receive a number. Likewise, you use DNS to find the IP address associated with a domain. In short, DNS is user-friendly, scalable, and decentralized. Now, I'll explain the key components and functions. DNS involves a series of interconnected components. Each plays an important role in the efficient resolution of domain names. Here's an example DNS resolution process from a server perspective to help explain. The process starts with a user query. They want to visit sophos.com and enter the FQDN in their browser. The user computer checks if the info is cached in its local DNS. If found, the process stops here and the web page will load. If the user computer doesn't have the info cached, it communicates with a DNS resolver, which could be local or public. This either responds from its cache or begins the resolution process. If the DNS resolver doesn't have the record either, it queries the root DNS servers to identify the authoritative DNS server for the top-level domain, or TLD. Next, the resolver queries the TLD DNS servers to discover the authoritative servers for the second-level domain. Finally, the resolver queries the authoritative DNS server for the specific domain to obtain the IP address associated with the requested name. This is then communicated back to the user device to load the website. In this process, we see four components of the DNS ecosystem, which represents a client-server model. The DNS client, which is the end-user device, and the DNS server that responds to the client queries. We also see the recursive DNS server, which is the local DNS resolver that handles the client queries. Finally, there is the authoritative server, which is responsible for storing and providing authoritative DNS records for specific domains. Authoritative DNS servers are administered into different DNS zones and subsequently manage them. There are two types: forward lookup zones, which map names to IP addresses, and reverse lookup zones, which map IP addresses to names. The DNS resolution process relies on the collaboration of these components. The client-server model ensures that DNS queries from clients are efficiently handled by servers. Recursive servers, or local resolvers, interact with authoritative servers during the resolution process. Authoritative servers organize into zones all the DNS records needed for the translation of domain names into IP addresses. Now, I'll walk through the DNS structure and hierarchy. Understanding this is essential for effective domain management and the proper function of the Internet. The hierarchical structure ensures the organization of domains into zones, defines authoritative DNS servers, and categorizes domains based on their top-level domain associations. To illustrate this, I'll use the example domain cloud.sophos.com. This hierarchy is crucial for efficient and scalable domain name resolution and has the following layers. At the top of the hierarchy is the root domain, represented by a dot. This isn't part of any specific top level and serves as the starting point for the DNS resolution process. The next level is the top-level domain, or TLD. TLDs appear at the end of domain names. They can be generic, like .com, .org, or .gov, or represent a specific country, such as .mx, .ca, or .au. These are known as country code TLDs or ccTLDs. Moving on, we have second-level domains, which are directly to the left of the TLD. In the example, this is Sophos. Lastly, we have the subdomain. Subdomains can be extended nearly infinitely since each one can have its own set of subdomains. In our example, this is cloud. The fully qualified domain name, or FQDN, is the sum of all the domains we discussed. For example, the FQDN would be sophos.com, but we can include the subdomain too. So that's cloud.sophos.com. A fully qualified domain name represents a specific location in the DNS hierarchy. Now, let's discuss DNS zones. The overall domain hierarchy is organized into various zones that allow you to manage and control them independently. The primary zone is a read-write copy of the DNS database for a specific domain. The authoritative DNS server for the primary zone is responsible for maintaining and updating the zone's DNS records. Changes to the DNS records, like additions or modifications, are made on the primary DNS server. Think of this as your DNS host server. Then there's the secondary zone. This is a duplicate of the primary zone and is used for fault tolerance and load distribution. And finally, there are zone files. These are text files corresponding to each DNS zone or domain that contain information about the DNS records. They include the most crucial part, the mappings between domain names and IP addresses or other type of records. Now, let's return to our previous example to explain the query process. I'll break down the DNS lookup steps. As seen before, when a user enters a URL into a browser, the computer initiates a DNS lookup to find the IP of the website. The computer first checks its local cache. If no DNS info is found, the computer sends a request to the IP configure to resolve DNS queries. Usually a DNS domain controller or a public, well-known DNS resolver, such as 8.8.8.8. The resolver follows the same process, checking its own cache and internal DNS records. If nothing is found, it contacts the configured forwarders or root DNS servers. The root DNS servers direct the resolver to the corresponding top-level domain server. The TLD server then redirects the resolver to the authoritative DNS server for the specific domain. Then, the authoritative server provides the IP address, which is passed down to the user device. The information is stored in the local cache for future use, and by now, the website should be loaded. This process illustrates a DNS query and answer. There are two types of each. The first query type is a recursive query. Here, a DNS resolver or client requests information from the DNS server and expects a complete answer. The DNS server performs all necessary steps to gather the information from root servers to authoritative servers and provides a final answer to the client. This is what we saw in the example. The other type of query is iterative. The DNS resolver requests information from the DNS server, but expects the server to provide the best information it has. The DNS server may not have the complete answer and can either provide the available information or refer the resolver to another DNS server. As mentioned, there are also two answer types that can be provided by DNS servers. An authoritative answer comes directly from a DNS server that has the official and complete information for a specific domain. The example shows this type, and this is what's expected for most queries. And a non-authoritative answer comes from any DNS server that may have cached the information, but is not the official source for that domain. It's considered less accurate. So, the type of answer received depends on whether the queried DNS server has direct access to the authoritative DNS server or not. As a final note about queries, I'll discuss the role of DNS forwarders and time to leave, or TTL. DNS forwarders are servers that forward DNS queries from one server to another. Instead of querying the root servers and following the entire DNS resolution process, a DNS server can be configured to forward queries elsewhere, usually an ISP's DNS server or a public DNS server like Google's or OpenDNS. TTL is a value in the DNS record measured in seconds. It indicates the maximum length of time that information should be cached by DNS resolvers or other devices. Once this time expires, a new DNS query must be performed. The last topic I'll cover is the various resource record types. Resource records act like a directory for DNS, specifying how domain names relate to IP addresses, mail servers, and other domain-related functions. Each type serves a specific purpose in facilitating the smooth function of the domain name system. These are some of the most common resource records. An A record translates a domain name to an IPv4 address. As discussed earlier, navigating to sophos.com maps to an IP address which uses an A record. An AAA record is the same as an A record but is used for IPv6 addresses. A CNAME or canonical record works as an alias for another domain or subdomain. For example, if you have one firewall, which is the point of entry for multiple services, you may have mail.sophos.com and backup.sophos.com pointing to the alias firewall.sophos.com. An MX or mail exchange record points to the mail server responsible for receiving emails on behalf of the domain. Mail servers will look up MX records in order to properly send mail to one another. An NS or name server record identifies the authoritative DNS servers for a domain. A PTR or pointer record performs a reverse DNS lookup, translating an IP address back into a domain name. A TXT record is typically used for verification purposes only. Lastly, the SOA or Start of Authority record contains essential information about a DNS zone, including details about the domain's management. So that covers the fundamentals of domain name systems. I hope you found this useful. This is just a brief overview, so check out the relevant resources for more information about DNS. For further assistance, view and post questions on community.sophos.com and go to techbits.sophos.com for more great videos like this one. Thanks for watching!